Do y'all have that? Does everybody have that sheet we were working on, the electron configuration, periodic table, the trends sheet? Because I have some extra copies if you need it. Okay. Last week, we had done effective nuclear charge on the front page, and we had done atomic radius. And so now we're on the back page. We first talk about ionic radius. Now, y'all have heard me say a whole lot this semester that with chemistry, we got to know the lingo. Yes? What do I mean by that? I mean, when I say ionic, you got to know. What does ionic mean? Or ion?
Anything that is lost electron or gained electrons.
Okay. Ionic means it's lost electrons and it's gained electrons, right? It could be either or. So an ion is something with a charge. So, I mean, real quick, when I say you should know this, you ought to be just bam, 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 I get it. What's a cation?
Positive.
Positive. How does something become a cation? Loses electrons. Okay, if it's not a cation, then it is an anion, and it has what charge? Anion? Negative. And what does it have to do with electrons? Y'all are scaring me. It gains electrons. Okay. Now, also, and this is kind of per what Tyler and Ashley, what we were talking about at the beginning, like chemistry's comprehensive, and what do you need to know? Do you guys remember the marble in the stadium? I talked about that analogy way back in chapter 2, and I brought it up again last week. Tell me what that analogy is, the marble in the stadium.
If the marble was the nucleus with all the protons and neutrons, the stadium is where all the electrons are.
Yes. So where's all the mass of an atom? In the nucleus. What determines how big around the atom is? The electrons. So they take up most of the space. Now, knowing that, if you have something like magnesium that's neutral, how many protons does magnesium have? 12. How many electrons does it have? If it's neutral, 12. What kind of charge does magnesium form? +2. What does it have to do to form a +2 charge? Has to lose 2 electrons. What is that going to do to how big around it is? It's going to make it smaller. So there you go. What goes in that first blank? Cations are always smaller. Exactly. They're always smaller because they've lost electrons, and electrons are more responsible for how big around the atom is. Okay, so, oh man. I didn't know that I lost play. Okay, cations are always smaller. What goes in the next blank? Anions are always bigger than their neutral atoms. And then I put a little diagram on there. Do y'all see how you've got that? Oops. I've got that diagram of here's the lithium and here's the little fluorine. And what happens is, y'all, lithium is going to transfer an electron to fluorine in that diagram. And when it does, it makes lithium have a +1 charge, and it makes fluorine have a -1 charge. And you can see, I mean, this would have been even better if I could draw them with colors, and you can see the purple one change in size and the little black one change in size. Maybe I didn't draw them as well up here as they are on your sheet, but nonetheless. Okay. More positive the cation means it's lost more electrons. So what's that going to do to its size? The more positive the cation, smaller it is. So smaller goes in that blank, and the more negative the anion, the larger it is. Okay, how is ionic radius, the trend we're doing right now, different from atomic radius, the trend on the previous page? They're talking about different things. What's atomic radius talking about?
The size of them on the periodic table.
Okay, it's the size of them when they don't have a charge, right? But ionic radius is the size when they have a charge. So that's the difference. Okay, now, next trend, ionization energy. Definition is there on your sheet. Ionization energy is the minimum energy required to remove an electron from a gaseous atom in its ground state. Okay, key word here, y'all, really, it's removing an electron. That's the key word, because ionization energy, if you will just briefly look at electron affinity, what's electron affinity doing with electrons? Adding them, okay? So we're going to talk about that next. But first, let's do ionization energy. How much energy does it take to remove an electron? Let me rewrite on my handout what you've got on your sheet, on my iPad what you got on your sheet. If you take a sodium, and so we're starting there, we got sodium gas. If we strip an electron away from that, then the product side shows the electron stripped away. It's a sodium ion, and then we show the electron separate from that, okay? On your sheet, I have that labeled as an I1. Alex in the book is probably going to call it an IE1, where of course IE stands for ionization energy. And the fact that it has a 1 on it is talking about removing the first electron. The IE1, and it's right there on your sheet, you don't memorize this, it's 495.9 kilojoules per mole. Now, if I took that sodium, see that already has an electron removed, and I remove another electron from it, that's going to give sodium a +2 charge. And I would, again, on the product side, show that that electron has been stripped away. And this would be an IE2, which is 4,560 kilojoules per mole. Okay? Now, y'all, what charge does sodium like to form? +1. And you know that because it's in group 1 of the periodic table. And so we just learned group 1, sodium likes to do this. Does sodium form a +2 charge? No, sodium doesn't like to do this. Look at these energies. IE1 is 495.9. Do y'all see that the IE2 energy is 10 times the IE1? 10 times 49.5 is going to be 4,900. So that is about, technically I guess it's 9 times. It's 9 times this. That's a huge jump in energy from IE1 to IE2. That tells us sodium is not going to do this. It's not going to form a +2 charge because it takes too much energy for that to happen. We can explain this by looking at sodium's electron configuration. Y'all, sodium's electron configuration is, I'm going to write the long-handed version, okay? It's 1s2, 2s2, 2p6, 3s1. Or you guys know that the shorthand version of that, the noble gas, would be neon 3s1. Y'all also know that its electron orbital diagram looks like this: 1s, 2s, 2p, 3s. Do you see that this IE1, it's removing this electron right here? That electron that's out there by itself. Do you see that that little electron out there by itself, does it make sense to you guys that it wouldn't take a lot of energy to remove that one? Because it's all by itself. So if I remove that one, then this is where I'm at. I'm trying to erase it. Keeps flipping. Okay. This is removing an electron like it is now. Do you remember learning about Hund's rule and about Pauli exclusion principle? This right here, 1s2, 2s2, 2p6, is very stable. It takes a lot of energy to remove another one. That's why it's not going to happen. So a lot of these ionization energies can be explained by examining the electron orbital diagram. Okay, and why there's a jump. Okay, so here, let's see if you can take what I've done and apply it to something else. All group 1 elements are going to see a jump in ionization energy as you go from IE1 to IE2. Where's the jump going to be for a group 2 element? Between IE1 and 2, between 2 and 3, between 3 and 4, what? Where's the jump in energy going to be for an element in group 2?
Oh, why is it from 2 to 3?
You're exactly right. It's from 2 to 3. Group 2 likes to form a +2 charge. Y'all, the fact that they like to form a +2 charge means it's really easy to take the first electron away. Really easy, that's relative. It's really easy to take the second electron away because they form a +2 charge. But to remove a third electron, group 2 doesn't form a +3 charge. So they experience a jump between IE2 and IE3. Now, when we're looking at the trends for ionization energy, the trend for ionization energy is all about the IE1 trend. Okay, so what you're about to write is for IE1. And look, here's the trend, represented 2 different ways. We're looking at only the representative elements. These are all IE1. Look at the numbers. As you go from left to right, what happens? It increases. That's what goes in the blank as you go from left to right.
I have like 50 different pins if you want one.
Yeah, check this out.
Okay, what happens as you go from top to bottom? It decreases. It gets smaller or it decreases. Okay? You're talking about the energy required to remove an electron. Less energy, like cesium, 376. Y'all, less energy means it's easier for it to happen versus lithium, 520. So cesium will more readily lose an electron than lithium will. Guys, do you see that what that's telling you is cesium is more reactive than lithium? Definitely, if you're going to strip an electron away, cesium would be way more reactive than lithium. Can you give me an answer for why that is based on another trend we did? How come do you think it's easier to remove an electron from cesium, takes less energy, than from lithium?
Because it's smaller.
Which one's smaller?
Cesium, right?
Other way. You're exactly right. Lithium, the diameter of a lithium is smaller. Remember, size increases as you go down. And so we're talking about removing the valence electron. So the valence electron from cesium is further from the nucleus. And the nucleus is what is giving it that electrostatic charge to hold on to the electron. And so the fact that cesium is a bigger round atom, that's why it's easier. It's easier to snatch an electron away when it's further from the nucleus. Okay? This little graph is showing you the same thing as this periodic table. It's just got numbers. But like for here, lithium, this is second period, right? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay? Go ahead.
And how come some atom, or like iron is more reactive than gold, even though iron is smaller? Or is it?
Okay. You have to consider the d orbitals in that. That is why when we look at the trends, we do not consider the transition metals, because the ionization energy of the d orbitals, because These, like scandium through zinc, those are in a 3D orbital. Y'all know that. What that actually means is that their orbital is closer to the nucleus than a 4s orbital. The 3D orbitals, it changes everything. It also changes, we're not here yet in the lecture, but I think you'll know what I'm talking about. The octet rule. What's the octet rule mean? Everything wants to be 8. Because, and we haven't done this yet, so this is just jumping ahead. Because of the d orbitals, some elements can actually handle 10. Because they have d orbitals. So the d orbitals, they can handle 10 electrons.
10
Like number 10, not TIN, sorry. They can handle 10 electrons, and we'll have more than an octet. And some of the smaller ones, like boron, they don't even want an octet. They want less than. So, there's always exceptions.
And the ionization energy thing is excluding all transition metals.
Yes, all of these trends are.
Okay.
All of these trends is only the representative elements, groups 1 and 2 and 13 through 18. Okay, but let me see if y'all can explain something else. You can look here. As you go, first ionization energy, lithium's 520, beryllium's 899, boron's 800. We just wrote that it increases left to right. How come there's a drop right there? Look, happens again from magnesium to aluminum. Not as big, but it still happens. Why is it dropping there? And then look what it does. It climbs again. Oh.
Is it the thing where like you have to move it up one or something like that? Cause like,
I need more.
This one's,
Okay.
two go in one spot.
Yeah. So watch. Lithium and beryllium. Do y'all agree these, oh shucks. Lithium and beryllium, it's its 1s orbital full, right? This electron that it's removing right here on boron, y'all know that these are the 2p orbitals. Yes? This electron right here for boron, it's removing that electron. So as you go from beryllium to boron, boron looks like this. It's real easy to remove that one because it's in a p orbital all by itself. And then when you move over to carbon, carbon looks like this. There's some stability there. Hund's rule says if we spin on the same direction, there's stability. So that one's harder. If I do nitrogen, nitrogen looks like this. Higher energy, 1402, stability. As you go from nitrogen to oxygen, the energy drops down. Why? Where is that electron right there? It's 2p, 1, 2, 3, 4. Right there. It's easy to remove this one spin in the opposite direction. So a lot of these little flexes in ionization energy can be explained with the orbital diagram.
could I take a picture of that?
Yeah.
Or would you rather me not?
No, I don't care. It's right here. I'm recording this too.
Oh, okay.
But it's in your book.
Okay.
That's where I'm getting it from. Okay, the next trend is electron affinity. And read the definition. The negative of the energy required to add an electron to a gaseous atom or ion. What is if an energy is negative, what does that mean?
It's released.
It's releasing, it's exothermic. Okay? Y'all, electron affinities is a measure of the energy released. Oh, hang on, I think I'm really zoomed in. The energy is released, but when we look at the trends, it's the negative of that energy, so that you're just looking at the positive numbers, if you will. And it's the energy release when you add an electron. Guys, on the periodic table, which elements like to have an electron added to them?
17, third group,
Yes, group 17. How do you know that?
because they like forming negative one charge.
Because they like forming -1 charges. Group 16, they actually like to have 2 electrons added to them because they form -2 charges. Okay, so here is your trend for electron affinity. Hang on. That little page break really bothers it.
What about, how come the bottom ones aren't used, like, from francium to UUO?
Okay, those are, why isn't that like period 7 stuff? Why isn't it showing up on here? Because everything in period 7 is radioactive. And because all of those starting like with 104 on, those are all only created in a lab. They're not naturally in the earth. So, I mean, people, yes, they work with radioactive elements, but you're not going to look at that on trends.
And usually, like, the ones created in the earth, that they are not, like, they're created
Not
in the lab.
natural, created in the lab.
Are they usually, like, stable or not?
They're very unstable. They're actually rather fleeting. Okay, they exist only for a short amount of time. That is why all of these have their mass numbers in parentheses,
Yeah.
because they don't even exist long enough to get an accurate atomic mass of them, because they decay.
What about 61 and, like, 43? The same with them?
Or 61.
On
Yeah.
the bottom two?
Yeah, they're radioactive. Remember, all the white ones are man-made elements. Yeah, and they're radioactive. Okay, here is your electron affinity. Remember, this is the negative of the number. So these are all releasing energy, but we just look at it as positive numbers. What is the trend going left to right for electron affinity? What's happening to the number?
It's, like, weird.
It's weird. Left to right, the trend increases. It's really hard to see on this one because there's so few electrons you're dealing with. Maybe you can see it a little more here. 42, 134. Yes, there's a blip. Then it starts increasing again. Left to right, it increases. Top to bottom, it decreases a little bit, but it's just not a lot of change, top to bottom. Okay, y'all, look at group 18. Does group 18, what do we know about group 18?
No, again,
Noble gases, what else do we know?
there's no, the 8, they like to
They're, everything likes to have 8 electrons in its outer shell. They have 8.
stable.
They're very stable. Do they have an electron affinity? Do they want electrons? Does a noble gas want more electrons? No, it's very stable. So when we say that the electron affinity, the number increases left to right. If I were to ask you in the third period, what third period element has the highest electron affinity? What third period element has the highest electron affinity?
Sulfur.
It's
That one didn't say, sorry.
chlorine. You would never pick a noble gas for the highest electron affinity. Okay? Yes, electron affinity increases left to right, but noble gases never have the highest because they don't want electrons. Okay? Now, let's look at electronegativity. Read the definition. Electronegativity, it's the ability of an atom in a bond to attract electrons to itself. Y'all, electronegativity is a measure of what elements hog electrons. Okay? Because some elements like electrons more than others. The trend for electronegativity is it increases bottom to top and increases left to right. And what is electronegativity? It's in a bond, which atom hogs the electrons more. That's it. Now, let me attempt, I'm gonna ask y'all a question that you might see as a trick question, but it's not, because it fits the definition. What element is the most electronegative element? It's not a race to get the answer. Look at the trend. What element is the most electronegative element?
That's not electronegative.
No, that's electron affinity up there. Is it helium?
Or would it not be because it's a
What
noble
would
gas?
you
Or would it not be because it's a noble gas? Yes. What is the most electronegative element? If electronegativity increases bottom to top and left to right, most electronegative element has got to be top right. But it's not helium because it's the ability of an atom in a bond to attract electrons to itself. Helium doesn't bond. The most electronegative element is fluorine.
So
It's not a noble
reactors,
gas.
They don't bond.
They do not bond. Noble gases are excluded from the trend because they do not bond.
Only this trend though, they're excluded from.
And the electron
So
affinity
you
trend.
only find them in like pure.
Yeah, noble gases are only monoatomic. It's just NEs. It's not Ne2s or Ne3s. It's just neon, monoatomic. It's just argon. Okay, interestingly, look. Up until the 1960s, y'all, the noble gases were referred to, they were called inert gases. What does inert mean?
They don't react.
Means they don't react. In the 1960s, in a lab, scientists made a noble gas react. They made xenon react. Why'd they pick xenon? Well, do you guys agree, excluding radon, that xenon would be the biggest around noble gas? Okay? Because size increases as you move down the periodic table. Since xenon has the largest radius, that means the valence electrons of xenon are further from the nucleus, so they're going to be more easily stripped away than, say, in helium, where the nucleus is really close to the valence electrons and it's holding them tighter. The first noble gas that was made to react with xenon, guess what they reacted it with? They picked fluorine to react it with because fluorine is an electron hog. And the first compound ever formed from a noble gas was XeF4, xenon tetrafluoride. And they reacted it with the most electronegative element. Huh?
How much energy did it take?
I have no idea how much energy it took. I have told you all I know about the first compound was xenon tetrafluoride, and that's when the trend or the acceptance of calling them inert gases changed to, let's just call them noble gases, because they do react. But-
And do you know why they use xenon instead of radon?
Because radon's radioactive. Safer. Okay?